Welcome to my channel Sharath NEET Academy. See, yesterday we have discussed force acting on a charged particle when it is moving in a uniform magnetic field. Yesterday we have discussed motion of a charged particle inside the magnetic field when we project with an angle 90 degrees. See, when a charged particle is thrown inside the magnetic field at an angle 90 degrees, then it revolves in a circular path. Okay, when it is revolves in a circular path, its radius is constant. Kinetic energy is constant. These are all we have discussed. But now what we are doing, we are projecting this charged particle into the magnetic field with an angle 90 degrees from outside. For example, if I throw a charged particle, positively charged particle, in this direction, positive charge is moving in this direction means current also goes in this direction. Magnetic force, see here, magnetic field is into the board, current is going in this direction, so force will act in this direction. So on this charged particle, force will act in this direction, magnetic force. Okay, so it will go in resultant direction, so it will come out like this. So that means whenever we throw a charged particle into a uniform magnetic field with an angle 90 degrees, yesterday only we have discussed, we have thrown like this or like this or like this, doesn't matter. It is a normal projection. 90 degrees even can be called as normal, even that can be called as orthogonal. So when we throw a charged particle from outside the magnetic field into the field, then it traces a curved path. We have to draw an imaginary circle, then you will get the radius of the circle. Okay, sometimes in competitive exams, we may throw with a certain angle with the x-axis, not with the magnetic field. With the magnetic field already it is 90. With the x-axis or maybe with the y-axis, we have thrown with certain angle. Then with what angle it will come out? These kind of questions we may face in competitive exams. This concept I will discuss in detail when we discuss the numericals. Okay, when we throw inside, it traces a circular path. When we throw from outside, it follows a curved path. No doubt, if you draw an imaginary circle for this, here also you will get circle, but particle may not go in a circular path. Particle goes in an arc. Here tangential, it will go out in a tangential direction like this. It will go like this. Okay, this is another important point you have to remember. Okay, we are going to throw a charged particle into a uniform magnetic field with an angle other than 0, 90, 180. Angle other than 0 degree, 90 degree and 180 degree. Okay, between we have so many angles, 5 degree, 30 degree, 50 degree, 120 degree like that. We are not going to throw with 0, we are not going to throw with 90, we are not going to throw with 180. We are going to throw with other angles. So then what is the direction of magnetic force and which path the charged particle follows, that we will discuss now. See here. To understand this concept, I am going to represent magnetic field along the x-axis, not along the z-axis. Into field is negative z-axis, out field is positive z-axis. Here I am representing magnetic field along the x-axis. Now I would like to throw a charged particle, positively charged particle in this direction with certain velocity, making an angle theta with the magnetic field. Now see, this angle is neither 0 nor 180. It is not neither 90 degrees. It is acute angle, lies between 0 and 90. If we throw like this, then what will happen? See, this is very important. When velocity vector is making certain angle with x-axis, I can resolve this velocity vector into two components. Component should not go beyond this. Remember, this is a proper representation of resolution. Sometimes we may draw a bit longer, sometimes we may draw with a bit smaller, but perfect resolution is this. This is horizontal component. This is the vertical component. Okay. When we resolve two components, components must be perpendicular to each other, and parent vector, the vector which is resolved, must be lies between these two. Okay. After that, the name of the components are obviously v cos theta and v sin theta. When v is resolved, we'll get v cos theta, v sin theta. When f is resolved, we'll get f sin theta, f cos theta. But which is cos, which is sin is going to decide by this angle. Okay, when angle is here, this is adjacent, this is opposite. When angle is here, this is adjacent, this becomes opposite. So adjacent one is cos, so v cos theta. Opposite is v sin theta. This is important. Okay, this is not always v cos theta, this is not always v sin theta. If theta is here, no doubt it is v cos theta, it is v sin theta. If I take here theta, then it becomes v cos theta, this becomes v sin theta. Remember this. Okay, now the magnetic field is represented in this direction. Okay. Now I would like to apply Fleming's left hand rule for this charged particle to know the direction of magnetic force. So magnetic field is in this direction. Magnetic field is in this direction. Now actually charged particle is moving like this. It is moving along the x-axis as well as along the y-axis. It is moving in a plane. So who is responsible for traveling along the x-axis means v cos theta. V cos theta is taking the charged particle along the x-axis. V sin theta is taking the charged particle along the vertical component, vertical direction. Okay. So now I am going to apply magnetic force for components. This is the magnetic field. A charged particle which is moving along the x-axis moves with a velocity v cos theta. The angle between velocity and magnetic field is 0 in this case. Magnetic force Fm is equal to Q into velocity is v cos theta. Magnetic field is B, and the sine of angle between velocity and magnetic field here is 0. So that's why magnetic force is 0. Okay, so for this component there is no magnetic force. Okay, for this component magnetic force I will calculate Fm is equal to Q into velocity is v sin theta, magnetic field is B, angle between magnetic field and velocity is 90 degrees, sine 90, so force is maximum, this is 1. Then you will get force is QVB QVB sin theta will get. For this there is no force. Force is 0 along this component. So acceleration is 0. So V cos theta remains the same. V cos theta remains the same. But here component is V sin theta, charge is positive, magnetic field is in this direction. In the direction of motion of positive charge we have current. So current finger we have opened, but it is like this. Then you open this finger, then you will understand force is acting into the plane of the board. Magnetic field is in this direction, current is going upward, so force acts inside. Force will act inside. So this magnetic force, see here, velocity vector, velocity, component of velocity and magnetic field are making 90 degrees. So path traced by a charged particle is circular path inside. See, component is like this, charge is like this, force will act this side. So charge makes a circular path like this. Is that okay? This component makes the charged particle to move in a circular path. But V cos theta is acting along the direction of the magnetic field. That means this charge is influenced by this component as well as this component. This component makes the charged particle to revolve in a circular path. But this component pulls the charged particle in this direction. So that's why the charged particle, due to vertical component, it will be like this. For horizontal component, it moves like this. It moves along the x-axis as well as it makes a circular path. So that's why the path traced by a charged particle is helical path. Helical path. The charged particle will go like this. Here it is very important. Radius of the circular path remains the same. Radius of the circular path remains the same because V sin theta is constant. Here the magnetic force which is acting towards the center acts as a centripetal force. This centripetal force develops a centripetal acceleration. This is accelerated motion, but this acceleration and this force are involved in changing the direction of the charged particle. Magnitude of velocity remains the same. That means speed remains the same. So speed remains the same, but direction is changing. So velocity changes. Velocity changes means acceleration is there. But this centripetal force, magnetic force and magnetic accelerations are changing the direction of the charged particle. So radius of the circular path remains the same. So radius will be remains the same. Without increasing the radius, this charged particle moves along the x-axis because V cos theta component is taking the charged particle forward. Okay, when we project a charged particle perpendicularly, there is no horizontal component, then the charged particle makes a circular path here only. It will stay here only. It will never go anywhere because here only this component is experiencing force. So here charged particle will rotate here only. It will never move forward. When a charged particle is projected with certain velocity by making an angle theta, then this will have vertical component as well as horizontal component. Vertical component makes the charged particle to revolve in a circular path. Horizontal component pulls the charged particle forward. So the charged particle have combined motion, circular motion as well as a linear motion. So it will have combined motion. So the path traced by a charged particle is called helical path. Helical path. This is even can be called as helix. Okay, in this way the charged particle will move. When a charged particle is moving in a helical path, even we have to answer so many questions. Those will answer one after the other. See this. And one more important thing I would like to explain here. See, whatever may be the angle of projection, when I project with zero angle, force is zero, acceleration zero, velocity remains the same, particle is tracing straight line path. There also kinetic energy same, their velocity remains the same. If you throw with 180 also velocity is same. Even when you throw with an angle 90 degrees, the particle is revolving in a circular path, but speed of the charged particle everywhere same. Velocity is a vector, direction changes, velocity changes, but speed of the particle is same. Even you throw with a certain angle other than 0, 90 and 180, it is following helical path. See, whichever the angle you throw in the magnetic field, it doesn't matter. Speed of the charged particle remains the same, you see. Here speed, v cos theta constant, v sin theta constant. So resultant velocity, v is equal to root over v sin theta whole square plus v cos theta whole square. It becomes again v. Okay, that means this is very important observation we made by projecting in different angles. Whatever may be the angle of projection, a charged particle never increases its speed. So kinetic energy remains the same. That means magnetic force does not increases the kinetic energy of the charged particle. Here the magnetic force is utilized only to change the direction of the charged particle. This magnetic force never increases energy of the charged particle. Very, very important point, remember. Okay. See, when the particle is revolving like this, then we may come across various questions. That is again radius of the helix. Radius of helix. Helic or helix, whatever it is, helix. Radius of the helix means this is the radius. This is the radius of the helix. This is the radius of the helix. Who is responsible for this radius? V sin theta. V cos theta is taking the particle along the horizontal direction. So radius of the helix, reason is V sin theta. This even I can call it as a perpendicular component of velocity. This is horizontal or parallel component of velocity. So radius of the circular path we know, that is mv by qb. This we have already studied. But their velocity of projection itself is making an angle 90 degrees. That's why we got directly v here. But here the perpendicular component is responsible for circular motion, circular path. So that's why here radius of the helix I am going to represent with r is equal to mv perpendicular divided by qb. Okay, this perpendicular component in this case is v sin theta. So radius of the helix can be written as mv sin theta divided by qb. This expression is true for only this diagram. This expression is true for any diagram. Why I am saying like that? Because if I take angle here, this is the vertical component. This vertical component becomes v sin theta. If I take theta here, this is vertical component, but it becomes v cos theta. When I take angle here, then this expression is mv cos theta by qb. But in both the cases, this is only the vertical component, so v perpendicular is always right. Okay, this is the radius of the helix. Radius of the helix. After that, we need to find pitch of the helix. Pitch of the helix. What is this pitch word? See, this is we have studied in screw gauge, head scale, pitch scale we have studied. So pitch of the screw means the distance travelled by a charged particle before completing one revolution. Before completing one revolution. Pitch of the helix means the distance travelled by a charged particle before completing one revolution. See, charged particle is beginned here, it completes one revolution. So when charged particle moves from here to here, then it completes one revolution. So the distance between these two spirals is called pitch of the helix. This I can calculate by using formula horizontal component of velocity into time period of revolution. Time taken to complete one revolution is called time period. So pitch is a distance. Distance can be we can get it from velocity into time. So who is taking the charged particle in this direction? V cos theta is taking in this direction. So V cos theta into time period. So pitch of the helix is V cos theta into time period. Okay. So horizontal component, even we can write it as parallel component. Okay, na horizontal component into time period can be called as pitch of the helix. This is always right. This is maybe we don't know whether it is a V cos theta or V sin theta, but for this diagram it is V cos theta. Okay, that means to answer this question we need to get a time period of revolution. See, time period of revolution of a charged particle in the helical path is the same as the previous 2 pi m by qb. Why? Because time period of revolution of a charged particle is independent of velocity and radius. So that's why time period of revolution when it is thrown perpendicular or when it is thrown with certain angle doesn't matter, it is remains same. So this is the time period of revolution of a charged particle even when it is projected with an angle other than 0, 90, 180, time period expression is same. So pitch of the helix will get V cos theta into 2 pi m by qb. So this is the pitch of the helix. Time period and even frequency both are remains the same. Frequency is 1 by time period. This can be written as qb by 2 pi m. qb by 2 pi m. Even omega is qb by m. Okay, now these are all same. Additional thing we have learned here is pitch of the helix. So all the concepts are related to a charged particle is projected into a magnetic field with an angle other than 0, 90 and 180 also covered in this. Okay, this is how we will measure everything. So after all covering these concepts, important conclusions are: a charged particle is thrown into a uniform magnetic field, it experiences force, but in two cases it will not experience force. When it is thrown parallel to the magnetic field, force is 0, anti-parallel to the magnetic field, force is 0. In all other cases, it will experience force. Force formula: magnetic force acting on a charged particle is QVB sin theta. QVB sin theta. By applying this, we will come to know the magnitude. The direction of force can be known by using or maybe right hand thumb screw rule. Okay, here whichever is comfortable in the given application, you can follow that. In the next video, we are going to cover the numerical problems based on this concept, force acting on a charged particle in a magnetic field, that we will upload on Monday. See, what we have observed with all this, whatever may be the angle of projection other than 0 and 180, magnetic force will act. That magnetic force is only used to change the direction of the charged particle, that's it. That magnetic force never increases the speed of the charged particle. Okay, that means magnetic force in magnetic field, a charged particle never increases or decreases its kinetic energy. Kinetic energy remains same. This is important thing. Magnetic force is utilized to change the direction of the charged particle. That's it. You remember, this is very important. Okay. So after all covering all these concepts, if you like the way of explanation, and presentation, you please subscribe the channel and you recommend your friends to watch this, and you please recommend, like and share. Thank you.